record here and bring up this file. Do you have any particular place you want to start today?
I was thinking maybe we could just go over some questions on what's on that sheet.
Okay.
So just like random question in each of those fields.
We kind of started in the middle of this. Let's see. We started after you check marked. Word problems involving trig ratios. All right. Come up with one of those.
Let me get paper.
Let's say that there is a building and you're standing over here 20 feet from the building and you take a surveying instrument and you measure a 28-degree angle. How do you figure out the height of the building? I'm sorry, what?
So, sorry, I'm just getting paper up. Okay, so you have to use the law of...
No, this is a right triangle. You never have to use the law of sines or cosines on a right triangle. And most word problems are going to be...
Oh, wait.
They're going to be right triangles because word problems tend to be telephone poles, buildings, mountains, all of which are right triangles when viewed from the side. Okay.
Right.
So we're not going to use, we don't solve this problem with the law of sines, even though we do have three pieces of information. We have one angle, another angle, and this distance. So theoretically we could, but that's the hard way to do it. Try to figure out, when you're working with right triangles, figure out the trig function that relates that to that. And then begin.
All right, so I'm going to fill in that last angle just for the hell of it. 62.
Okay. Don't need it, but.
So the sine of... No, it's not the sine. It's the tangent of 28 will give you h.
There you go.
Right?
And always, well, it gives you what? What is the tangent of 28 degrees? In other words, always finish your equation based on your SOHCAHTOA. What's the tangent of 28?
It's 8 over 20.
There you go. Which makes h equal to 20. Oh, I hear we're having a little audio problems here. Have you heard everything I've said, you think?
Yes.
Oh, okay, good. Okay, so that's a typical word problem. And it can, of course, be structured all kinds of ways. It could be, let's change it a little bit. And I'm going to say we're 20 feet away from the building, and the building is 10 feet high. What is theta?
The theta is sine. It's going to be the tangent of theta is 10 over 20.
Good. That's the way to start it. And then,
so tan of theta is 1/2.
So theta equals what?
Theta equals...
If the tangent of theta equals 1/2, what's theta equal? I mean, how do you get it?
You use the inverse tangent.
Of 1/2, correct.
Of 1/2, so it's 26.6.
Right. So with right triangles, all you need is two pieces of information to figure out everything. if we wanted to figure out this angle up here, then the tan of theta would be 20 over 10, and theta would be the inverse tan of 2. Okay, so all of these problems are going to be fairly straightforward if they just involve a word problem where they give you 2 pieces of information and ask for the third. They can get a little tougher, but I don't know that I've ever seen you have a problem like that. In other words, let's say there's a building in the distance and you don't know how far you are from it, but you take a angle measurement to the top of that building and that turns out to be 20 degrees. And that's the only thing you know. And the question is how tall is the building and how far away are you from it? And obviously you cannot solve that. In other words, I can say the tangent of 20 degrees equals 8 over x. 2 variables, can't solve it. But if I go in 100 feet and take another reading, and this angle ends up being 30 degrees, now that allows me to write a second equation involving h and x. What is the second equation?
30 tangent of 30 equals h over x minus 100.
2 variables, 2 equations. You can solve for both x and h.
Okay.
Now, do you have any questions as to how to solve for x and h there?
Yeah, I don't think I know. I mean, maybe once, if you try to do it, I'll know how, but I don't think I know how to do that.
All right. Well, all of a sudden my thing stopped writing. It did. Hold on. Let me open it and close it. So we had the tangent of 20 equals h over x, and we had the tangent of 30 equals h over 100. 100 minus x or x minus 100? It's x minus 100.
Yeah, it's x minus 100.
All right, so solve for one variable and then substitute in the other. In other words, solve the left equation for h. So h is going to be x times tan of 20. Okay?
Okay.
Go to the second equation and substitute for h. So I have the tan of 30.
Tan of 30 equals x tan 20 over x minus 100.
Yeah, now there's only one variable in that one.
Okay.
And of course, the next step is to go ahead and put numbers on the tan of 30 and the tan of 20, and then you would have x minus 100 times the tan of 30 equals x times the tan of 20. And then, since these are just numbers, then it becomes a straight algebraic equation. You have to distribute, gather your x's on one side. You want to finish the problem out?
Sure.
Give me numbers on tan of 30 and tan of 20.
I'm going to just finish writing this. Tan of 30 equals x. Okay. So tangent of 30 is 0.58.
So I'm putting it in front because it's a coefficient. And what's the tan of 20?
Equals x. 20 tan is 0.36.
0.36?
Yes.
Okay, now we have just an algebraic equation. So I'm going to distribute. So I get 0.58x minus 58 equals 0.36x. I'm going to bring the x on the right over to the left, giving me 0.22x, and I'm going to take that negative 58 and move it to the right. And now x is going to be 58 divided by 0.22. Which is like 250, something like that.
263.
263. And x was the total distance to the building.
Right.
So that's probably as hard as they get in terms of right angle word problems, where you end up with two equations and two unknowns. Have a look at this thing again. What's the angle of inclination?
1 and 4.
Just 2.
Oh.
Just 2.
Yeah, 2 and 4.
In other words,
2 and 3.
When you're talking about looking up, you're only talking about angle of inclination. Okay? Where did I just see that? The meaning of angle of elevation. I'm sorry, I didn't mean inclination. The angle of elevation and the angle of depression. 2 is the angle of elevation. What's the angle of depression?
Angle of depression would be
3.
Oh, okay. Well, aren't they the same thing, though?
Well, they are. The only difference is that if you have a word problem where somebody is standing on top of a building pointing down, then this is the angle they're talking about.
Okay.
If you have somebody on the ground aiming their surveying instrument up, this is the angle they're talking about. And because the two horizontal lines that I drew are parallel, yes, they are the same. So either one, in other words, whether you had somebody on top aiming down or somebody on bottom aiming up, they both produce the same triangle. And that angle is the angle of elevation and the angle of depression. But it's not this one.
Okay.
Okay? The best way to figure it out is always to start with the angle of elevation because you know that's it. It's theta. Okay? And if you know the angle of depression is the same angle, then it has to be that one there because those two are alternate interior angles on parallel lines. These pages, I'm wondering, do you have a textbook that's out of?
He gives us packets.
Okay, so
I don't have a packet. It is out of a textbook. It's
No, I have a textbook, and that's in the Trig section. I'm wondering if it's the same thing.
What textbook is it? Like what color?
Doesn't look like it. Well, it's yellow and blue, and it's by Demana, Waits, Foley, and Kennedy, called Precalc.
All right. I don't think that's the same one.
Okay, it doesn't really matter.
Ours is a Trig book, but it's
Okay, Yeah, it doesn't figure to be the same one because this book that I'm looking at starts out almost immediately in the unit circle. So clearly you guys are a little different.
Yeah.
I'm just looking in this book for problems. I'll leave it open and see if I need problems to find. I can look in my book and find it. All right, section 6.3. Evaluating trig functions for any angle using the reference angle and angle quadrants. And this is what we did yesterday, and you seemed pretty good at it. You comfortable with that? In other words, no matter what trig function I give you, no matter whether the angle is positive, negative, inside 360 degrees, or greater than 360 degrees, you can do it?
Yes.
What's that?
That is. Wait.
Yeah, don't use your calculator, by all means. In other words, this particular section is a non-calculator section. If it was a calculator section, there wouldn't be any point, you know.
Is it 920? I mean, 900, sorry.
Tell you what, let's not convert it to degrees. I mean, you can always do these problems that way. Let's think in radians.
Oh, okay.
How many multiple, what's a unit circle in radians? What's 360 degrees in radians?
360 degrees in radians is 2 pi.
Okay, so how many multiples of 2 pi can I take away from that to get it inside the unit circle?
2.
So what is this the same as? It's the sine of pi. In other words, I took away 4 pi.
Right.
Sine of pi is almost easier to remember. Well, I don't know. Do you have it memorized?
It's sine of pi is, wait, I know this. Wait, it's 1, isn't it?
No.
0?
First of all, there's 2 ways to do it. And one thing that is going to be really helpful to you at some point is if you've memorized the sine curve. And the key points on the sine curve are 1, -1, and then the 4 quarter points. By that I mean, well, first of all, if we go to the end, that's 2 pi. You're going to start working in radians here pretty soon. And so you're going to start labeling your x-axis in radians, not degrees. So from that graph, what's the sine of pi?
Sine of pi is 0.
Correct. As the sine of 0 is 0 also.
And 2 pi.
Yes. So this curve, I highly recommend you memorizing and memorize, like I said, these quarter points on there. What's that?
You memorize sine and cosine.
Yes. Let me draw the cosine. The biggest difference from the cosine is it starts at 1 and goes down. Right, and goes down. But it still goes to 2 pi. Still has the same quarter points. And goes between 1 and -1. Now, obviously, I've only drawn one period of each of these. And in reality, they continue on in both directions to infinity and negative infinity. But, so what's the cosine of pi?
The cosine of pi is -1.
Correct. So if you have these 2 curves memorized, you won't have any problems with your quadrangles. And this is the way I prefer to do it. If somebody asks me a question as to, what the sine or cosine of a quadrangle is, a multiple of 90, I always refer to these 2 charts. as opposed to the technique that I was talking about briefly. Did you fully understand that? When I was
Which?
Yesterday, when I was telling you that any point on the unit circle is the xy, the x is cosine of x, and the y is sine of x.
Yes.
Okay? So if I want to know what the cosine of 0 angle is, well, what's the points on that curve? That point is 1, 0. Therefore, the cosine of 0 must be 1, and the sine of 0 must be 0. So this is just another way to memorize your quadrants or your quadrangles. If I have a 90-degree angle, well, what's the points right there are 0, 1. So if I want to know what the cosine of 90 degrees is, it's 0. If I want to know what the sine of 90 degrees is, it's 1.
Okay.
Okay.
Yeah.
Now, what would the tangent, let me think for a second. What's the tangent of 0? First of all, what's the tangent and relationship to sine and cosine?
Sine over cosine.
Okay. So knowing that there's your cosine and sine, what's the tangent of 0?
Well, it's 0 over 1.
Which is?
Undefined.
Oh. You can divide into 0. You just can't divide by 0. That's the key.
It's 0.
That's the key difference. Yes, it's completely different. Notice that there are opposite ends of the number line. In other words, 0 divided by 1 is a number. That's 0. But 1 divided by 0 is undefined, which actually means infinity. So it's infinitely large. So if you want to know your tangent of the quadrangles, you can either memorize the tangent curve, which is a little more unusual. You don't run into it as much. Or you can always just use this and know that it's sine over cosine. So what's the tangent of 90 degrees?
The tangent of 90 degrees is 1 over 0.
Which is?
That's undefined.
Correct. And that's why your tangent curve looks like this. Has two asymptotes. Starts from the bottom, always increasing, goes through 0 at 0, and these points are minus 90 degrees and plus 90 degrees. So tangent goes from negative infinity to infinity, and it's asymptotic with an asymptote every pi. In other words, multiple periods of the tangent are like that. And like I said, this is a little more unusual, so not everybody maybe memorizes that. And you don't necessarily need to memorize the tangent curve as much as the sine and cosine curve. All right, let's see. So are we good with the first part of this section, 6.3? You feel comfortable that you can do that?
Yes.
Using the reference angle and the angle quadrants. Okay. Expressing trig functions in terms of others using the Pythagorean identities. All right. First of all, there are 11 basic trig identities that are absolutely necessary that you know. So let's just go through them all. Let's talk about the reciprocal. Now, we don't need to spend a lot of time on these if you're really good on them. There's 6 reciprocal identities. What's that one?
Cotangent, cosecant.
Like that?
Yes.
Remember the word reciprocal. It's 1 over that.
Oh, okay.
Sine is not the same as cosecant. Sine is the reciprocal of cosecant, which makes cosecant also the reciprocal of sine. In other words, if you know this one follows. So, you know all 6 reciprocals?
Yes.
Okay. There are 2 quotient. What's tangent and cotangent? Quotient means that it's going to be a quotient on the other side.
A quotient?
Uh-huh. We just
So
sine x over cosine x.
And cosine x over sine x.
Right. Again, you get this one memorized, this one will follow. And finally, there are 3 Pythagorean identities. Not finally, because actually there's a ton more, but you may or may not have to memorize the others. These 11 you definitely have to memorize. Okay, what's the first Pythagorean identity? And Pythagorean by definition means that this means where they're going to be squared. In other words, when you think Pythagorean, you think a squared plus b squared equals c squared. Okay, so we're looking for trig identities where stuff is squared. We'll start with sine squared of x plus cosine squared of x equals what?
That equals 1.
Uh-huh. No matter what x is, let's just delve into this for a moment. Let's make x equal 30 degrees. Okay? So what's the sine of 30 degrees? In fact, what is that if I substitute 30 degrees for x?
Sine of 30 degrees is
Don't use your calculator on any of these until we get to angles that are not multiples.
Okay. Isn't it 1/2?
Correct. So what's this? What I've circled is what?
So it's 1/4.
Okay. What's the cosine of 30 degrees?
3 pi over 2.
No, there's no pi in any of these. These all come from those 2 special triangles. And remember one thing. Trig is always about ratios. Trig functions give you ratios. So it's going to be hard to get a pi in there. Unless the only place pi would come in is in the angle. I could have referred to this angle instead of 30 degrees, I could have said pi over 6. But the trig function of an angle is not ever going to have a pi in the answer. What's the cosine of 30 degrees? Based on, if you forget it, then you want to make sure you have this triangle memorized. This is always your fallback, because you can always figure out any trig function for 30 or 60 degrees. What's the cosine of 60? Excuse me, this cosine of 30.
Square root of 3 over 2.
Okay, so square root of 3 over 2 squared, right? In other words, cosine squared of x means cosine x times cosine x. So that's why I take the cosine of x and square it. Well, what's square root of 3 over 2 squared?
Square root of 2, it's 3 over 4.
1/4 plus 3/4 equals 1. And it does not matter what angle I use. I could have made x 60 degrees. I could have made x 42 degrees. The sine squared plus the cosine squared is always equal to 1. What's the second Pythagorean identity? Starting with
Second Pythagorean.
there's 3 of them. Second one starts with tan squared of x.
Tangent squared x plus
1 equals,
I don't know.
secant squared.
Okay.
Okay? Just as important as the first one. And you'll need it as often. And there's a third one, but the third one is, you don't have to memorize, because the third one is the second one, only with the cofunctions. Instead of the functions tan and secant, I'm going to use the cofunction, cotan and cosecant. So the third one, same format as the second one. In other words, it's plus 1. And they're both quite different than the first one. Now, the Pythagorean identities, you don't always see them like this. You may be solving a trig identity question and you get something like this. What's that equal to?
So secant squared x minus tangent squared x. What is that equal to? So that's equal to, is it -1?
No. How do I alter this middle equation to get secant squared minus tangent squared? How about if we subtract tangent squared from both sides?
Okay, I'm sorry. I'm a little lost. So we subtract tangent squared from both sides.
And I've got
that
secant squared minus tangent squared equals plus 1.
Oh, okay. Okay, that makes sense.
So my only point...
It's weird for me treating them like they're regular numbers.
Well, you've definitely got to memorize these 3. But what I'm saying is that your tests are going to be harder than that, because you're not always going to see it in that form. You might see it in that form. So you have to be able to figure out how we got this. And if you start with tangent squared plus 1 equals secant squared, well, you can realize that we got this by subtracting tan squared from both sides.
Okay.
Same thing with the top one. More often than not, you see this or this. What's 1 minus sine squared equal to?
1 minus sine squared is equal to cosine
squared.
Cosine squared, yeah.
And 1 minus cosine squared?
Equal to sine squared.
Right. Okay, so again, you're more likely to see 1 minus than you are to see this.
Right.
And there's a whole batch of trig where... Have you done verifying trig identities yet?
I don't think so.
Okay.
I mean, maybe, but it doesn't sound familiar.
There's no practical world purpose for verifying trig identities.
Okay.
It's an exercise that is designed to get you to memorize your 11 Pythagorean or your 11 trig identities. Your 6 reciprocal, your 2 quotient, and your 3 Pythagorean. And you know, I think it helps to break it up like that. Instead of memorizing 11 things, let's memorize 6 things, 2 things, and then 3 things. Okay. In my mind, it always makes it easier to access if I have it compartmentalized. Okay. And verifying trig identities is very valuable when you're trying to learn trig, because by the time you get done with doing like 50 problems, you'll have all 11 of those memorized.
Yeah.
I mean,
Okay,
that's the purpose it actually serves. Now, it is true that there are real world problems that have trig equations in them. I might have a real world problem that said sine squared x plus cosine x times secant of x equals 10. Well, in that real equation, I'm going to substitute 1 for sine squared plus cosine squared, always. So there are trig equations that describe real world problems, and to solve them, you need to know your identities.
Right.
That's
right. I get that I need to memorize them.
Yeah. All right. Let's see what else we got here.
Is that all of them?
That's the 11 important ones. I'm just going to go down this page. There are others, but I don't know if you've had them or not. I can just briefly ask, have you had sum and difference?
No.
Okay. Let's not get to those yet then.
Okay.
There's also double angle. In other words, the sine of 2x is equal to 2 sine x cosine x.
What is that helpful with if you an angle?
Say, yeah, if you wanted to know the sine of, let me think for a minute. The double angle isn't nearly as useful as the half angle. In other words, there's also the sine of a half angle x. And this is useful. Say you wanted to know the sine of 22.5 degrees. Well, you would use the half angle if you didn't have a calculator. And it's always based on, let me make sure I'm not giving it to you wrong. My focus doesn't get into the... Well, you know what? If you haven't had it, let's not even talk about it.
Okay.
Okay. Well, I mean, I have no problem talking about it, but if you have a test coming up and there's certain material you need to know, let's just cover that material. Okay. Pythagorean identities, expressing trig functions in terms of others. Okay, I don't know how else further to cover that. Expressing trig functions in terms of others using the definition of trig functions. Not quite sure what they mean by that.
Oh shit, expressing trig functions in terms of others.
Of using the definitions of other trig functions. I guess you'd be able to figure out that the tangent is equal to the sine over the cosine. In other words, I think this is what they mean. Tangent equals the sine, which is the opposite over the hypotenuse, over the cosine, which is the adjacent over the hypotenuse. Solve that fraction and you get adjacent over opposite. So we could always figure out what tangent was, as long as we knew the tangent was the sine over the cosine, and we know the sine is opposite over hypotenuse and the cosine is adjacent over hypotenuse, and the tangent is sine over cosine, that makes the tangent adjacent over opposite. or excuse me, opposite, I wrote it wrong. It's opposite over adjacent. When I solve this problem, I flip this and multiply. So I get O over A.
Okay.
They may mean some other things there, but I'm not sure exactly what they mean. However, applying the formula of an area of a triangle, we can certainly do that. Now, this is where we're getting away from right triangles. Just a second, let me make sure. That's something else I rarely do is, oh, here we go. Yeah, let me just point out what I wanted to say before. The sine of x over 2, which is a half angle identity, is plus or minus the square root of 1 minus cosine x over 2. So, if you wanted to say find the sine of 22.5 degrees without a calculator, well, that's the same as the sine of 45 degrees divided by 2, correct?
Right. Okay, so you get the sine of 45 degrees and you divide that by 2.
And the only thing I need is the cosine of 45 degrees. This x is the numerator. So it's equal to plus or minus the square root of 1 minus the cosine of 45 degrees is square root of 2 over 2. There we have our answer. I can simplify that answer, but basically I can figure out some trig functions of particularly unusual angles by using the half angle formulas.
Okay.
So you have double angle, you have sum and difference, and you have half angle. Those are the next identities that you would likely learn if you're going to go there. I'm not sure that they necessarily are going to take you there. They may not cover all of these. Let's talk about the area of a triangle. I know one thing and one thing only. No, I gotta know more than one thing. Just a second.
Yeah.
I gotta know the two sides also. In other words, I could solve this entire triangle using the law of what? Sine or cosine, right. Well, I'd start with the law of cosines, and then I'd finish it using the law of sines. But that doesn't help me solve for the area right off the get-go. In other words, area is base times a vertical height, right? And I don't have the vertical height here. So there are three area formulas. The area of a triangle is 1/2 side B times C times the sine of the third angle, A. It's also 1/2 times A times C times the sine of B. Notice all three letters are on the right side. Two of them are side lengths, one of them's an angle. And this last one would be AB sine of C. So as long as you have two sides and one angle, you can use one of these three area formulas to solve for the area of this. Let's put in some numbers here. What would the area of that triangle be?
The area of that triangle would be, so A equals 1/2 6 times 7 sine of A, or sine of 40.
Correct. And you can see that each of these three is a side angle side. In other words, you use this when you don't have a vertical height. Well, actually, you only use this when you have exactly side angle side.
Okay.
Yeah. If there's another area formula that is you use when you have only three sides. However, from the page, it said only that one. And when it says only this one, it actually means all three that I wrote. In other words, all three of these kind of go together.
Well, they're the same thing.
Right, they are the same thing. It's just that you know a different angle. In the second one, I know angle B, and I know side A and side C.
Right. It doesn't actually matter.
But it's still side angle side.
Right.
There is something called Heron's formula that applies when you have side, 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 and you want to know the area of that triangle. And I'll just run it by you to see whether you've had it or not. It's a little different. It's the semi-perimeter is what S stands for, times the semi-perimeter minus one side, times the semi-perimeter minus the other side, times the semi-perimeter minus the third side. In other words, let me change this number to a 9, first of all. The perimeter is 22.
Okay.
So the semi-perimeter is 11. Half of the perimeter. And I got 11 minus 9. I got 11 minus 7. And I got 11 minus 6. So that also gives me the area of a triangle if I have side, side, side. It's interesting, I hadn't thought about it before, that these area all are done when you have to use the law of cosines with side, angle, side. This area is done when you would have had to use the law of cosines with side, side, side. And that's the only two situations where you have to use the law of cosines.
Okay.
Okay? Even though they're not really related.
I knew the top one. I definitely didn't know the bottom one.
Yeah, well, maybe they're not going to cover this one. I haven't seen it yet in your material. In other words, they only refer to this one in this line here.
Yeah.
So it's always going to be side, angle, side. Okay, find the angle given one of the trig functions evaluated at theta. This is fairly straightforward. I'll just throw some at you. Sine of theta equals 4/7. How do you solve for theta?
You multiply both sides by 7?
Nope.
No.
Here's the key. When you use trig functions, you get ratios. When you use inverse trig functions, you get angles. So if you're solving for an angle, you're going to have to bring an inverse trig function in there.
The inverse sine of 4/7.
Right. In other words, by definition, that's what that means. And as you saw in the ambiguous case of the law of sines, you would want the first and second quadrant angles. Do you have your calculator handy?
Yes.
Do that one. Do the inverse sine of 4/7.
So you get negative 34.8.
No, that's a positive number, not going to be in the fourth quadrant. And you're not going to get a negative answer.
Oh, I don't know what I did, but okay.
Maybe you need to use the parentheses. In other words, you need to take the inverse sine, left paren 4 divided by 7, right paren.
It's giving me, okay, now 34.8.
Okay. So it only gives you the first quadrant answer. Notice. But there is another perfectly legitimate answer. That's the second quadrant answer. In other words, whatever is supplementary to this angle, 145.2. So always know that your calculator is only giving you one of the two answers in the unit circle, because there's always two quadrants that have the same plus or minus sign. Same thing with cosine and same thing with tangent. Cosine is going to give you first quadrant answer only, but you can also figure out the fourth quadrant answer, which is the other place that cosine is positive.
Okay.
And this only really comes into play when you're solving that ambiguous case of the law of sines, and then this number here becomes pretty important, because that's what tells you whether or not you have the ambiguous case of the law of sines.
All right.
Now, another way to look at this, if you forget, it kind of is helpful. If we take the inverse sine of both sides, when you take the inverse sine of the sine, you get theta. Well, if I did it to the left, I got to do it to the right. So theta is equal to the inverse sine of 1/2. Now, they may give you problems like, maybe not, but if you see anything, have you seen anything that looks like this?
Doesn't
Notice that that is an angle, right?
Right.
So there's no x that goes out there. In other words, that's theta. So this really is the sine of theta. So you'd want to work from the inside out on this. What's the inverse sine of, or the inverse tangent of 1? It's 45 degrees. So this problem becomes this. And that's square root of 2 over 2. Okay, so this concept is, I can't stress it greatly enough, which is inverses are always done with numbers, trying to find angles. Trig functions are always done on angles, trying to find numbers or ratios.
Okay.
You haven't seen anything like this, but you may have seen stuff like this. Sine of the inverse sine. And then you always know that it's going to be that. That's what's left when you do that. Either way, if I take the sine of an inverse sine or the inverse sine of a sine, I get what's that. That's what it is left after I do that. I don't know that you actually have to think that way to solve these. The best way to really solve them is we take sines of angles and we take inverse sines of numbers. In other words, these two statements are if and only if. If the first one's true, the second's true. If the second one's true, the first one's true.
Okay.
All right.
Okay, so that is everything that's on the
Okay.
test, I believe, right? So
Well, that's the only thing on this paper, yeah.
right.
Is this entire test covering just through section? Is your entire test just going through section 6.4?
I think so.
Okay. Well, we can certainly practice and drill on these 4 sections tomorrow if you like.
Yes, absolutely.
Okay. Well, let's do that then.
All right. So
I got plenty of problems in my books, and now I know exactly what we're covering. I can just give you problems, and tomorrow we'll do more problems than explanations.
okay.
Okay?
So tomorrow at 12.
Tomorrow at 12 your time, which is 10 my time. Yeah.
Okay. Awesome.
Okay? Max, I'll talk to you then.
Thank you.
Bye-bye.